Hello everyone, and now let's look at our last example of a relative rates problem. So now I'm in prison because that super fast cop caught me, so of course I miss Will and I'm wishing for martini. I'm stuck in prison now. But there's a TV, so I'm watching the TV. On the TV, there's a show about a rocket being launched into space, maybe from Tesla or so SpaceX, sorry, or maybe from Amazon. And to see or witness this marvelous progress of science, there's a camera that is 1,200 meters away from the launching pad to follow that rocket. So, of course, the camera must be looking at the rocket at all time to witness this marvelous event. The vertical speed of the rocket stays constant at 180 meters per second. To record correctly the rocket, we need to keep track of the distance between the camera and the rocket for the zoom and the angle between the rocket and the camera and the ground in order for the camera to pivot correctly and look at the rocket. So when the rocket is at 900 meters high, fine. So two questions in this question. So it's really the last two examples here. The rate of change of the distance between the camera and the rocket, again for the zoom. And then for the B part, we'll find the rate of change of the angular, or we'll find the angular velocity or the rate of change of the angle theta of the camera in order for the camera to be looking at the rocket. So if it's not turning, okay, it's not going to be very fun. So as usual, I already pre-drawn for you what's going on. So we have the ground here, we have a launching pad, we have a rocket that is traveling vertically above that launching pad. We have that camera that is 1,200 meters away from the launching pad. I decided to do it on the left. You could do this question on the right. It really does not matter. That quantity is fixed. So the base here is fixed. So what's going to change here? So as the rocket is traveling upward vertically, that distance between the rocket and the ground will change, and of course the distance between the rocket and the camera will also change. So we need variables for those two things. So those are the easier variable to work with. So let y be the distance between the rocket and the ground. So here visually, y would be that blue line. I'm going to use y here. We know right now, might as well put that information on. We know right now that y is 900. And of course, that distance here is actually increasing. So another fact that we can add is that this quantity is increasing as time goes by. The rocket will be higher and higher. So another variable here, the distance between the camera and the rocket. So we're going to call that distance. I like to use Z for like distances that are not horizontal or vertical. You can use X if you want. It really doesn't matter. I just don't like to use my X too much. Okay, so here you go. So let Z be the distance between the camera and the rocket. So here on my picture, Z is going to be that quantity right here. Do we know that quantity? Well, it's not given at this point, but you can see that Z is the hypotenuse of a right triangle. Whoa, what a surprise here. So by using Pythagoras' theorem, you can compute. So by going 1,200 squared plus 900 square rooted. I'll let you do that as an exercise, but right now, the value is 1,500. And the last variable that we need here, because we're looking at angular velocity, so the rate of change of an angle here. So we're going to use theta for the angle. So here the angle, I'm going to illustrate that in red. So this is going to be theta. And you can also, I forgot to mention this for Z, but Z is an increasing quantity as time goes by. Theta will also be an increasing quantity. All right, so all variables are labeled correctly. Now let's talk about rate of change. So for both questions, the rate that is given that we're going to use for both questions is the speed of the rocket, which is the rate of change of the variable y. So this means that, poof, dy dt is 180 meters per second. So here this quantity is, of course, positive because my variable y is an increasing value. All right, so now let's just focus on part A first, and then we'll do part B. All right, so the first question is to find the rate of change of the distance between the camera and the rocket ship. So because Z is that distance, the one that we're looking for is dz dt. So this question, this first part A is very similar to already two examples that we had. So first, we need to find an equation that links all the quantities together. Big reveal here. Okay, we're going to use Pythagoras' theorem. So here we go. So poof. So by taking the base squared, which is 1200, which will expand to 1,440,000 plus y squared is equal to z squared. So that's my equation that links the variable. But remember, the goal is to find an equation that links the variables and their rates. Okay, so related rates here. So the next step is to compute the derivative on both sides. Here, I strongly suggest when you have a constant to a certain power to get rid of it because this is just a constant. So when you're going to differentiate on both sides, I'm going to start with the 1200 squared. Or if you just remember that some fixed number squared is a constant, it's just to avoid the common mistake when people see like to the power 2, they tend to go like, oh, the power 2 goes down and blah, blah, blah. So anyway, so let's differentiate on both sides. So here, you start with your equation. Okay, so you have your equation and you're differentiating on both sides. So I'm just going to add the ddt on both sides. So very, very similar from earlier. Okay, so there's really no big difference here. We have again those power 2 variables. So when you're going to compute the derivative, the constant will go to 0. The y squared will go to 2y dy dt, and the z squared is going to go to 2z dz dt. Poof. So that's the equation that links all the variables and the rates together, the most important equation in a question like this. So now if you isolate dz dt simply by dividing by 2z on both sides, so you're going to get or create a formula for dz dt. Poof. So dz dt is y over z dy dt. And the only thing you have to do now, the reason why I'm taking the time to isolate, to isolate dz dt, is now I can just plug in my numbers. So here we go. So you just replace the y by 900, the z by 1500, and the dy dt by 180. So you're going to get that. Poof. So that's my numerical answer at the end, is that dz dt is going to be equal to 900. Is going to be equal to, so if you compute this number, poof, you're going to get 108 meters per second. So that's the rate of change of the distance between the camera and the rocket, also known as the relative speed between these two objects. Again, for that one, for part A, very similar question that we already dealt with 2 times. Will's ladder was a right triangle. Me and the cops going to that intersection was again a right triangle. This question, a camera and a rocket, is again a right triangle question. The next question is slightly more interesting for sure. So what are we looking for in part B? We're looking for the angular velocity, also known as the rate of change of the angle. So poof, the rate that we're looking for in part B is d theta. dt, and that's the one that is missing in this question. So we're trying to find that one. So first we need to find a formula that links theta with the other variables. So here either y or z. Because z was really the star of part A, I'm going to try to find a formula for theta that links theta with the other variables that uses whatever's given to us. So we had to compute the actual value of z right now. We had to compute dz dt. So is there a way to create a formula that links theta with what's given? So what I mean by this is when I look at my right triangle, to get a formula for theta, I'll have to use a ratio, either a sine ratio, a cosine ratio, or a tan ratio. And when I look at this right triangle, for sure, one of the side that is the best to use is the base here. The base is a very nice side. Why? Because it's a constant. So whatever ratio I'm going to use to define a formula that links theta with something else, I'm going to use the adjacent side. So either a cosine or a tangent. I'm not going to use a sine ratio. Now, which one do I choose? The hypotenuse or the opposite side? Again, here between the opposite side and the hypotenuse, the one that is all given to us is the opposite side. We had to compute. So if you make a mistake in the computation of z or in the computation of dz dt, potentially you're going to get something that is wrong for theta or d theta dt. So here the two best side to use in order to construct a ratio for theta is the opposite side and the adjacent side. So the best ratio that involves these two sides. So the formula that will link theta with another variable here will be tan theta. Poof. So again here, this is just to make my life safer. You could use a sine ratio, you could use a cosine ratio, but the sine ratio or the cosine ratio will intertwine z in the formula. I think sine is the worst one, okay, because you're going to use y and z, so that's two different variables. So the adjacent side to me is very precious. So if you have to use a ratio between two sides in a right triangle and one of the side is a constant, if you want to simplify your life, use that side. Okay, so now that we have a formula that links theta and y, we're going to differentiate that formula on both sides. So we're going to compute d dt on both sides. So poof, so the sixth step is just to say, well, let's compute the derivative on both sides of that formula. So now this is where the implicit differentiation is starting. So tan theta is the trickier one. So we know the derivative of tan theta. So if you just focus on tan theta, it would be cos theta, it will be secant square theta. So tan theta goes to secant square theta. But theta is something that changes over time. So it's a formula that we don't know explicitly, but we know how to compute it using implicit ideas. So here there's a little chain rule. If you have tan of some shit, you're going to get secant squared of that shit times shit prime. So I have to use my little chain rule to get the derivative of tan theta. And then on the other side, the derivative of y is just 1. So on the other side, you're just going to get 1 over 1200 times, of course, y is a quantity that changes over time, so you need to multiply afterwards by dy dt. So the derivative of y over 1200 is 1 over 1200 times dy dt. So you need to spit out that dy dt. So now when you look at this, since we're looking for d theta dt, I'm going to send the secant squared on the right side. So be careful when you have like secant squared, remember, okay, so secant theta, just a couple of remarks here. So secant theta is 1 over cos. So if you write secant squared as 1 over cos squared, you can multiply by cos squared on the right side, and then you have a formula for d theta dt. So you can isolate d theta dt here. So here we go. Poof. So therefore, d theta dt is cos squared theta over 1200 dy dt. So remember, I'm just bringing the secant squared on the other side. It becomes a cosine. And now I'm ready to plug in my numerical information. So here for the 7th step. So we have for the 7th step, poof, that d theta dt is going to be equal to, so I'm just replacing everything that I know here. Well, we don't know theta, so here there's actually a trick. So let me just write down what we know here. So cos squared theta is a tricky part. The over 1200 is fine. The d theta is 180. We are looking to find a formula, a numerical value for d theta over dt. What about cos theta? We don't even have theta. You could compute theta, or you could also remember that cos theta is the adjacent side over the hypotenuse. So here we won't be able to escape it. We'll need the hypotenuse here. So cos squared theta. So what is the adjacent side? So right now, the adjacent side is given by the adjacent side is 1200. So I'm just going to use adjacent side over the hypotenuse, which is 1500. And all that stuff needs to be squared. So even if I don't know theta, I can just use its definition, adjacent over hypotenuse, and I'm getting that ratio. And now you have a numerical value. If you use your calculator, you can verify that d theta dt is equal to 0.096 rad per second. So slightly more trickier, of course, to find that d theta dt, but by finding first a good formula using a trig ratio that involves two sides, and typically when you have to use a trig ratio to find a formula for theta, always use a constant side if possible. So here I was focusing on the adjacent side and between the opposite side where almost everything was given to me and the hypotenuse where you have to compute stuff. I went for the opposite side, and then I did my implicit differentiation. So just be careful. Tan theta became secant squared theta d theta dt. The y over 1200 became 1 over 1200 times dy dt. In that formula, I had almost everything except secant squared and d theta dt. But when you isolate d theta dt, the cosquared, any trig ratio, if you have a right triangle, if you want a sine, a cosine, a tan, or anything else, just use your triangle and don't worry about the angle. Okay, you're going to be way more efficient that way. And then by plugging all the information inside the equation that relates the variables and the rates together, we were able to find our d theta dt. And again, here the number is positive, and we were expecting that. I forgot to mention this. Yeah, I did mention it. But yes, the angle is getting bigger as the rocket is getting higher. Okay. All right, so for that section, that's it. That's all. Let's go to the moon. Bye.